Welcome to Lecture 8 of Electrical Engineering 525. In this lecture, we will discuss Section 3 of Chapter 5, which is on tapered line sources. In Section 2, we learned about uniform line sources, and in this section, we'll talk about tapered line sources. Excuse me, I have those section numbers off. It was Section 1 was uniform line sources, and this is Section 2. So this is Section 2 of Chapter 5. And the difference between a tapered line source and a uniform line source is that a uniform line source has the current on a uniform line source has the same magnitude over the entire length of the line source, whereas for a tapered line source, the magnitude of the current is tapering off. In fact, in each of the cases that we'll look at, it's tapering off to zero at the ends of the line source. And so we will see what effect this is going to have. Briefly, what we're going to see is that the side lobe levels will be reduced through the use of tapered rather than uniform line sources. Which, of course, that's generally a good thing to reduce the side lobe levels, but the disadvantage is that it will broaden the main beam and consequently lower the directivity of the line source. And so we're going to see a number of cases of this in the example problems that we will consider right now. And then for the test, you will do a couple of problems very similar to the problems we'll be looking at in the lecture. And repeatedly, and in fact in every one of these problems, we will be looking at Table 5-2, which is in Section 2 of Chapter 5 of your textbook. So let's, after that brief introduction now, let's jump into this. We will look at Problem 5.2-3. First, it says that we have a 3-meter long broadside line source operating at 1 gigahertz, and it has a cosine squared taper for the current distribution. So what this means basically then, if you take the cosine squared, obviously the cosine of 0 is 1, and so if you square that, you still get 1. So the magnitude of the current at z equals 0 is 1, but then as this goes toward the ends toward either end of the line source, it will go to 0 as cosine squared. And so for that kind of a source distribution, we want to know the half power beam width in degrees. That's part A. And then in part B, we want to find the directivity in decibels. So, and every one of these problems, as has already been mentioned, we'll look in Table 5-2. And so if you look in Table 5-2 for the cosine squared current distribution, you'll find that it says that the half power beam width in radians is 1.44 times lambda over L. Now, we're told that L is 3 meters, so we write that down here. But what about lambda? Well, this source is operating at 1 gigahertz, and we remember, and this is an important formula for you that probably will not be on the formula sheet. You need to remember that lambda is c over f. So in this case, then, c is 3 times 10 to the 8th meters per second. Actually, that's always the case, but in this case, f is 1 times 10 to the 9th hertz, which is, of course, inverse seconds. And so when we divide c by f, we get 0.3 meters. So lambda is 0.3 meters, and L is 3 meters. So the half power beam width then, since is 1.44 times lambda over L, that will be 1.44 times 0.3 meters over 3 meters, or 0.144 radians. And when you multiply that by 180 divided by pi, you can convert it to degrees, and you get that the half power beam width in degrees is 8.25 degrees. So just make sure on this problem that you can go to table 5-2 and see that that this is the formula that you have for the half power beam width in radians for a cosine squared tapered current distribution. Okay, and then from that to compute the directivity, again we turn to that same table, and there we get d over du. Now remember that du is the directivity for the uniform line source that we studied in section 1 of chapter 5. And so it tells us that the directivity is 0.667. So the directivity of this cosine squared tapered line source is 0.667 times the directivity of a uniform line source of the same length. Now, for a broadside line source, we have from equation 519 that du is 2 times L over lambda, as long as L is much greater than lambda. So in this case, this will become d equals 0.667 times du, which is 2 L over lambda. And again, L is 3 meters, lambda is 0.3 meters, and so this becomes 13.34. And when we convert that to decibels, we take 10 times the log base 10 of 13.34, and we get 11.25 decibels. So that's the directivity in decibels. And by the way, we will be using this table 5-2 for the broadside situation, not for the end fire situation. So that's why we're using the broadside formula that d sub u is 2L over lambda. Remember that for the end fire case, it's 4L over lambda, but we will not be using that in conjunction with table 5-2, only the broadside formula. So that concludes problem 5.2-3, and that's looking at one particular distribution. And now in problem 5.2-4, we're going to look at a number of current distributions, but in all of them we will be asking those same two questions that we considered in problem 5.2-3. That is, for each current distribution we will be looking at table 5-2 to get the half power beam width in degrees and to get the directivity in decibels. So really, this is quite a straightforward lecture with problems that are quite straightforward. The main thing that you need to do is, as you go through these problems, you need to make sure that you can look at the table and understand where the information in the lecture is coming from. You need to know where in the table to look. And of course, if we had a problem like this on the midterm exam or the final exam, the table would be provided to you. So just make sure as we go along that you understand the calculations and that you understand where the data is coming from in the table. So if you'll do that, then all of this is straightforward and we can look at it rather quickly. Okay, so remember now that in each one of the current distributions that we're about to consider, that the current distribution is assumed to be 10 wavelengths long. Okay, so in the first case we have the uniform distribution, and if you look in the table, it says that the half power beam width in radians for uniform distribution is 0.886 lambda over L. And so since L is 10 lambda, that becomes 0.886 times lambda over 10 lambda, or 0.0886. And if you multiply that by 180 over pi, you get 5.060 degrees for the half power beam width of a uniform current distribution of length 10 lambda. Now, to find the directivity, of course, for the uniform line source, d over du is 1, because du is for the uniform line source. That's what the u stands for. So d is in fact equal to du in this case, which again is equal to 2L over lambda from equation 519, and that's assuming broadside and L is much greater than lambda, which is an appropriate thing to use in this case since L is 10 lambda. And so if we take 2 times L over lambda, we get 2 times 10, which is 20. And then take 10 times log to the base 10 of 20, and we get 13.01 dB. And again, that's for the uniform line source of length 10 lambda. Now, in the next part of this problem, we look at the triangular line source. Now, keep in mind, the uniform line source does not go to 0 at the endpoints. It's uniform. It has the same magnitude throughout the entire length of the line source. But for all of the remaining ones, all of the remaining sources that we will look at in this problem are tapered line sources that go to 0 at the ends of the current distribution. So the first tapered line source that we will look at is the triangular line source. And if you look in table 5-2, it says that the half power beam width in radians for that is 1.28 times lambda over L. Again, L is 10 lambda, so this becomes 0.128. And when we convert that to degrees, we get 7.33 degrees. And you see that relative to the uniform line source, that the half power beam width is indeed larger, that main beam has been broadened, as was mentioned earlier. And what this will do is lower the directivity. In fact, you can see that from this equation here, the directivity is 0.75 times the directivity of the uniform line source. And so that's 0.75 times 2 L over lambda. Again, there we're using equation 519 to get that formula. And since L is 10 lambda, that becomes 0.75 times 20, or 15. And when we take 10 times log to the base 10 of 15, we get 11.76 decibels for the triangular line source. Now for the cosine tapered line source. In this case, again from table 5-2, the half power beam width in radians is 1.19 times lambda over L. And since L is 10 lambda, this becomes 0.119. We multiply that by 180 divided by pi, and we will get 6.82 degrees, which again is greater than the half power beam width of the uniform line source, which means that we have a broader main beam. And the directivity again is less than that of the uniform line source. In this case, the ratio of d over du is 0.81. So d is 0.81 times du, or 0.81 times 2L over lambda, once again using equation 519. So 0.81 times, since L is 10 lambda, this becomes 20. 0.81 times 20 gives us 16.2. And 10 times log to the base 10 of 16.2 is 12.10 decibels. In problem D, we have the cosine squared tapered current distribution. And once again, look in table 5-2 to find out that the half power beam width in radians is 1.44 times lambda over L, which since L is 10 lambda, that becomes 0.144. And if you multiply that by 180 over pi, you get 8.25 degrees for the half power beam width in degrees. And for the directivity, d over du is 0.667. So d is 0.667 du, which is 0.667 times 2L over lambda. Once again, equation 519. And since L is 10 lambda, this becomes 20, and 0.667 times 20 is 13.34. And when we take 10 times log of base 10 of 13.34, we get 11.25 dB. And then finally, cosine on a minus 10 dB pedestal. This is still another part of the table. If you look at the table, you'll see that the distributions of cosine on a pedestal are discussed at the bottom of page 140. Not discussed, but the listings, the data for those cosine on a pedestal taperings are at the bottom of page 140 and the top of page 141. Table 5-2 appears on both of those pages. So anyway, for cosine on a minus 10 dB pedestal, we find that the half power beam width in radians is 1.03 times lambda over L, which since L is equal to 10 lambda will become 0.103. Multiply that by 180 over pi, and you get 5.9 degrees for the half power beam width. And then if you look at the formula given for d over du, it is, or the value given for d over du is 0.92, which says that d is equal to 0.92 du, which is 0.92 times, once again, equation 519 gives us 2L over lambda. So 0.92 times 2 times L over lambda, which in this case is 2 times 10 or 20. 0.92 times 20 is 18.4. And 10 times log base 10 of 18.4 is 12.65. So the directivity of this tapered line source is 12.65 decibels. So you can see these problems are all quite straightforward, as long as you can, you need to remember to convert from radians to degrees. You need to convert to decibels. You need to, and you need finally to look in the right spot in table 5-2. So just make sure that you understand how to use that table, and you will be in good shape for problems of this type. And then we'll look at a couple of examples in the test for that lecture, for this lecture. So that's it. That concludes lecture 8 of Electrical Engineering 525, and good luck.